Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're continuing on with the LTAM course, going over the problems and the work solutions to the problems associated with the first half of Chapter 5. These are problems 4.22, 5.1, 5.4, 5.9, 5.10, and 5.11. So for 4.22, we're given that mortality follows the standard ultimate life table and deaths are uniformly distributed over each year of age. They give us interest, and they ask for the derivative with respect to t of a continuous increasing annuity on a 40-year-old for t years at t equals 10.5. So if we think of the increasing annuity as an integral, right, it's an integral because it's continuous, and we want the derivative of that integral with fundamental theorem of calculus, that just means we need the value, expected value, being added per unit time 10.5 years in. So for that, we know the face value will be 10.5, sort of. We know if you're still receiving payments, the face value will be 10.5. To convert from face value to present value, you divide by 10.5 years of interest, and you have to worry about mortality. And they give you deaths uniformly distributed over each year of age. Given how far apart these choices are, you actually don't even need that. Because when we crunch our numbers in, as it is, survival probability is more than 99%. And that's over 10.5 years. So the difference between 10 years and 10.5 years and 11 years is going to be like, I don't know, maybe 0.1%. Adjusting these by 0.1% would, let's see, by 10% would be like 0.6-ish, 1% would be 0.06-ish, 0.1% would be 0.006. So it really doesn't matter what assumption you use. As long as your survival probability is somewhere between the one for 10 years and the one for 11 years, you're gonna get answer C, the correct answer. But going through, after 10.5 years, face value is 10.5. You have to account for 10.5 years of interest. Survival probability is roughly 0.9917. You can find that one from the table. Multiply these together, you get 6.24. The trick to this, again, is to say, well, wait a minute, we didn't explicitly cover anything that said derivative of a continuously increasing annuity. That's okay. Derivative is just, since it's derivative with respect to time, that's just rate at which payments are coming in. Notice also the t is over here. It's the number of years that you're counting for. So it's just saying, what's the rate at which money is flowing in? And its face value 10.5 because it's an increasing annuity. Have to account for discount, and have to account for survival. Alright. 5.1. You're given a discount, force of discount and a force of mortality. And you want the present value random variable of a continuous annuity of 1 per year payable for the lifetime of X with 10 years certain. Have to calculate probability that Y is greater than its own expected value. So, first thing, we'll need to know what this expected value is. So we treat this as a frank annuity, right, because it's 10 years certain. So we calculate expected value of the first 10 years, which notice first 10 years, you ignore mortality completely. And then after that, you start realizing, yeah, now it depends on whether or not you survive. So for the first 10 years, it's just integral 0 to 10 of e to negative 0.06 t dt. Right? Hopefully you're comfortable with this sort of thing from exam FM. And after the first 10 years, you integrate from 10 to infinity, it's no longer just e to the negative 0.06t dt. You have to also multiply by e to the negative 0.01 t dt. So you get 7.52 for the first 10 years, 7.094 for the rest. Expected value of y is 14.614. All right, so we found e of y. Next thing we think about, we want the probability that y is greater than e of y. All right, so the longer you live, the more the annuity is worth. The longer you live, the more the annuity is worth. So we figure out how long you need to live for the annuity to be worth its average value, right? So if you live for t years, annuity value would be integral from 0 to t e to the negative 0.06t dt. Notice we don't have to throw in the mortality thing in here because we're presuming that you live for the t years, and then you don't. So our presumed mortality is actually 1 during this time. Sorry, our presumed survival, there we go, presumed survival is 1 during this whole time, and then 0 afterward. And we're saying if we know when you're going to die. So we know you're alive before then, and then we know you're dead after then. So you do the integral, get the function in terms of t. Algebra happens, and you get t. All right, so we figured out that y will exceed its expected value if and only if t exceeds 34.905. Lastly, we just say, well, survival function, okay, that's going to be e to the negative 0.01 times t, right? Because that's how constant mortality works with the survival function. And we crunch our numbers, and we get 0.7053, which is one of the choices. All right. 5.4. Russell, age 40, wins the SOA lottery. He'll receive both a deferred life annuity of K per year payable continuously starting at age 40 plus circle E40, and an annuity certain of K per year payable continuously for E circle 40 years. And you'll notice, yeah, we're going to have to figure out what E circle 40 is. Fortunately, that's not hard. Mortality is 0.02. Force of mortality is 0.02. And in your head, you should recognize that means circle E40 is 50. Right? When you have constant mortality, when you think back to exam P and remember how exponential distributions work, the average is just 1 over the force of decrement, or whatever this time constant is. They give you force of discount and the actuarial present value of the payments. And you have to figure out K. All right. So, as I alluded to earlier, you either do the integral or just recognize, yeah, E circle 40 is going to be 1 over mortality, but E circle 40 is going to be 50. So now, since the annuity is certain for 50 years, and life contingent for the rest, so for the first 50 years, you just say, all right, it's integral from 0 to 50 of face value of payment times discount. You get 39.347K. For the remaining time, it's integral from 50 to infinity of K times, now you need force of discount times probability of surviving that long. Or you need a discount factor times probability of surviving that long. So you multiply those together. Exponential, or product of exponentials is exponential of a sum, so you get e to the negative 0.03t. You integrate that, you get 7.438K. Total value is going to be 46.785K. We know that's equal to 10,000. Algebra happens, and you get K is about 214. So that's 5.4. 5.9. For select an ultimate mortality model with a 1-year select period, you're given that P selected at X is a little bit bigger than P sub X, right? 1 plus K for some small constant K. And you're given A double dot X colon angle N and A double dot selected at X colon angle N. and you have to calculate K. So we kind of use the 1 year recursions. But the way I personally viewed this is I said, well, let's break it down. I mean, if you think about where the 1 year recursions come from, there's the first year payment. That's guaranteed to be 1, right? Because you're getting paid right away. Then there are the other payments that are conditioned on survival. And because survival probabilities after the first year to year after the first, are the same, the only difference is survival probability for the first year. So when we can subtract 1 from each of these to get the expected values of everything past the first year, and that's what we do. So for non-select life, it's 20.854. For select life, it's 21.167. Now the ratio between these is going to be the ratio between survival probabilities. Okay? And since you're looking for the ratio, right, that ratio is going to be 1 plus k. You get that 1 plus k is 1.0150019. And I have an extra 0 here, don't I? This should be k equals 0.015, not 0.0015. Made a typo. One of these zeros should not be here. My mistake. But we get k is 0.015, which is one of the choices. Alright. So, problem 5.10. You have an annual life annuity due of 1 with a 5-year certain period on a 55-year-old. You're told that you can use the tables. Calculate the probability that the sum of the undiscounted payments actually made under this annuity will exceed the expected present value. Okay. So notice, sum of the undiscounted payments, that's just the number of payments. It's the number of years that you live. Number of years that you live rounded down, right? Because, oh, sorry, no, rounded up. Because if you live only half a year, you still get the first payment. So rounded up. All right. So first thing we want to do is figure out what's the expected present value. It's a Frank annuity. You Frankenstein it into the first 5 years and everything else. So for the first 5 years, you just do A double dot angle 5. Get 4.546. For the remaining time, it's a deferred annuity. So it's 5E55 times A double dot 60. Crunch the numbers together, you get 11.533. Add them up, you get 1608. So you need to survive 16 years in order for your payments to exceed this, right? If you survive 16.001 years, right? If you make it to January 2nd of that next year, then you'll still be receiving 17 payments. So if and only if you survive 16 years, the undiscounted payments will exceed the expected value. Crunch the numbers in. L71 over L55 gets you 0.9212. And that's one of the choices. So to recap, you first had to calculate the expected present value and then think, how many years would I need to live to earn more than that? Undiscounted. Okay. Lastly, for an annuity due that pays 100 at the beginning of each year that a 45-year-old is alive, you're given, for standard lives, you have the standard ultimate life table. They give you force of mortality for standard lives. They give you an additional penalty for being substandard, right? You just add this constant just for the first year. And you have to calculate the actuarial present value of this annuity for substandard life age 45. So it's kind of the opposite of a select life, right? You know this person is unhealthy. But it's only a 1 year not select period, or a 1 year adverse select period. All right. So you break it down. Standard lives will earn 100 right away, and then, looking ahead, you can look at A.46, right? 100 A.46. You'll figure out that they'll on average earn 1682 later. 100 right away, 1682 later. For the non-standard lives, you still earn the 100 right away, right? But now, your survival probability is a little bit lower. You're only 95.1% as likely to earn the remaining 1682. Or alternately, you could say, fine, I could take the natural logarithm of the ratio of, or negative natural logarithm of ratio of L46 to L45, add 0.05 to that, do e to the that much, e to the negative that much, and get the probability that way. But a shortcut is that when you're adding a constant to the force of mortality, notice you're just multiplying your probability by e to the negative that much. So you're 0.951 times as likely to earn the remaining 1682. Why do I have 1745 here? I believe this is a typo. Yes. My apologies. This 1745 should be 1682. But yeah, if this, I don't know where I got this from, but plugging in 1682 here gets the correct number. My apologies. Yes, bringing 1682, just mentally, like, roughly 5% off of 1682 means you subtract about 80, a little more than 80. So yes, that would work, yeah. So you get 1700. Apologies for, I don't even know where I got this from, but wherever I got it from, I recognized that I needed to fix it, but then didn't actually change this number here. I changed everything else and calculated it the right way. All right, so again, this 1745 should be a 1682. My apologies for that. And that's the solution to that one. As always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. Until next time, this is Dr. Nighttime wishing you a good night.